Hello, this is the second video for week 5. The first video was about lab 3, which is creating driving a 7-segment LED display. But this chapter is going into a little bit more detail about how we actually use Carnot maps, Boolean algebra, logic circuits, and truth tables in order to actually do stuff. Okay? And the chapter summary is here, right? So the first thing that you should be able to do as the chapter objectives is, given its logic diagram, know how to analyze a combinational logic circuit. Now the key word here is combinational. Okay, that a combinational logic circuit is one that doesn't have any memory. If it has memory, then we call it a sequential circuit. And we looked very, very briefly at a sequential circuit during lab 2, where we had the cross-coupled NOT gates, and you saw that it remembered what the input was even though you disconnected the input until you changed the input. You know? Two of the first circuits that just about every logic course looks at are the half adder and the full adder. What I'm asking you to do is to look at the textbook for the half adder and full adder, and I'll walk you through some of that now, but you need to read through it yourself too. Why are we looking at a half adder and full adder? Well, we've talked about number systems, and the lab 3 is about number systems. What do we want to do with numbers? Usually we want to do math with numbers, right? Computers are really good at doing math with numbers, so we want to see how we can build up towards how a computer does mathematics with numbers. And one of the most fundamental building blocks of arithmetic anyway is addition. So we're going to see how we can add a 1-bit number to another 1-bit number and get the right result. When we think about computers adding things, then things can go wrong, right? If I add a 1-bit number 1 to another 1-bit number 1, then the result of that addition is in decimal 2. However, if I'm only storing my information, my numbers, as a 1-bit number, I have a problem now, because 2 doesn't fit into 1 bit. In order to represent 2 as a binary number, I need to write it down as 1, 0. Right, so that's where the concept of overflow comes from. Underflow, similar idea, but now I might be subtracting 1 from another value 0, and then I get to -1, and I don't know how I represent that in a 1-bit number. The nice thing about the full adder, the half adder and the full adder, is that we can combine them together to make a 4-bit, 8-bit, 16-bit, 64-bit adder very easily. And so that's what the next step 4 there is about. Lab 3 is all about what step 5 is looking at. And once we've done that, then we might want to look at a different mathematical operation, and we'll look at the multiplier. So far we've talked about AND gates and OR gates and NAND gates and NOR gates. They're basic gates. But other integrated circuits are available that do more complicated things, like the 7447 BCD to 7-segment display decoder, right? That does a bit more complicated thing than what an AND gate or an OR gate or a NOT gate does. And there are other sorts of combinational logic circuits that also do complicated things. Decoders, encoders, priority encoders, multiplexers, and then we want to talk about a 3-state gate. The nice thing about a multiplexer, right, is that it gives us a really quick and dirty way, well, quick and easy way, shall we say, of implementing Boolean functions. And we'll talk about that. I'm probably not going to talk too much about these other items, because most of these other items are about either VHDL or Verilog, which is the way things like field programmable gate arrays are programmed in order to implement logic circuits. I will briefly touch on them in class, and I'll try and show you how an example one is programmed. But I'm not going to talk about that in this chat. Anyway, that's the introduction. I'm going to talk about the half adder in the next video, and then the full adder, and maybe we'll have a look at the 4-bit adder as well.